Hello and welcome to the video on section 3.5 exponential and logarithmic models. In this particular video, what we're going to be looking at is how to, number one, apply exponential growth and decay models to different biological, demographic, and economic phenomena. Number two, represent distributions with a Gaussian model. Number three, use the logistic growth models to represent a phenomena. Number four, use logarithmic models to solve problems such as species populations, credit card debt, and the wear-off of anesthesia. And number five, recognize and apply the appropriate model to each situation. Those are the things we're going to be looking at in this particular video. Now in terms of the models, the types of models we're going to be working with, one of the things we're going to be dealing with is an exponential growth. So in that case, we're going to be looking at something in the form of CE to the KT, where K is a positive value. And this a lot of times is going to look at population growth, especially if you have over a limited amount of time, bacteria growth, the appreciation, how things grow in value, and then you can even look at the spread of viruses in terms of as an exponential growth. The next one will be exponential decay. Now it's going to be the same model, but in this case K is going to be something that's less than zero. And when we're looking at this type of thing, we're going to be looking at radioactive decay, carbon dating, and depreciation. Now you're going to notice here when we say radioactive decay, carbon dating, we've talked about that before in terms of half-life. Now we're going to use this model instead of that half-life formula that we used before. The third type of model we're dealing with is a Gaussian model. And the Gaussian model takes this particular form here where it's f of t is going to be c, some constant c, times e raised to the negative x minus a, that quantity squared, all over some constant k. Again, though, in this case, c, a, and k happen to be constant values. And what you're looking at here, you would look at things like that, anything that could be represented with a bell curve, or might be a normal, what's called a normal data set. You could also look at life expectancy in terms of, you could also look at the average height and weight of people, and then intensity of laser beams, and even the IQ test would all fall under a Gaussian model. The fourth type of model is a logistic growth model, which is this one. F of t is a divided by 1 plus ce to the negative kt. Again, in this case, a, c, and k happen to be constant values. And the logistic growth model looks at things like carrying capacity in terms of a habitat. How many of an individual can it support? Also, if you look at the population growth over an extended period of time, especially where you have a situation where space and food happen to be limited, this is going to end up being a logistic curve. You could get into the spread of a virus also in this case, and things like you might have heard of a thing called a learning curve. That is also a logistic growth model. The fourth type of model we're dealing with is the logarithmic model, and that's things that could take this form here, or could get a little bit more complicated. You're going to see one later on that is might be a little bit more complicated. Not might be, it is a little bit more complicated, but we'll end up using it. And that is things like the population of species, looks at the paying off. How long is it going to take to pay off a loan based on the amount of payment, what payment you have, and the interest rate. Or things like the wear-off, like we talked about, of anesthesia, in terms of how, when you, think of when you go to the dentist and you have a filling done, they numb the tooth, and it takes some time for that to wear off, and that is also can be modeled. The amount of time it takes to wear off can be modeled with a logarithmic model. Let's start out here with an exponential growth, an example of that. So in 2000, the population of a town was 5,142. In 2010, the population was 5,951. Part A, what is the annual growth rate? And Part B, what year will the population reach 7,000 people. Well, in this case, we're going to use the model P of t equals P0 e to the RT, which is the exponential growth model. We've changed the letters a little bit, but we'll use P for population, R is your growth rate, T is time in years. And also in this case, we're going to let T equals 0 be to the year 2000. So that will help us out in terms of working with this. Now, in this case, I know in 2000 the population was 5,142. So I'm going to set my initial population, which is in the P0 spot, at 5,142. So right now I have P of t is 5,142 e to the RT. Now what I know in 2010 the population was 5,951. Well, because that's 2010 and 0 represents 2000, I know 2010 is going to be t equal to 10. So when I put 10 in for t, I know that's equal to 5,951 is going to be 5,142 e to the 10r. And so what I have to do now is solve it for the exponential. Remember when we dealt with these in the past, in the last section, we would solve for the exponential. So I get e to the 10r is 5,951 divided by 5,142. Taking the natural log of both sides, I get that the natural log of e to the 10r is 10r equals the natural log of 5,951 over 5,142. And when I put that into the calculator, that comes out to be 0.146117. Solving for r, dividing by 10, I get r equals 0.0146117, or r is about 0.015. So my growth rate r is 0.015, or about 1.5% per year. Now, in this case here, now that we know what r is, so I now have my model for this is P of t is 5,142 e to the 0.015 t. And what I'm going to do now is I need to solve that for, I want to find out what year it's going to be for 7,000 people to be in this town, assuming that everything stays consistent with what's been happening. So what I'm going to do is I'm going to say 7,000 equals 5,142 e to the 0.015 t. And I know what I need to do is solve for t. So I'm going to go through like we did before, solve for the exponential. I'm going to divide by 5,142. So I get e to the 0.015 t equals 7,000 over 5,142. Taking the natural log of both sides, I get that 0.015 t is about equal to 0.308468. Solving for t, I get about 20.56. So I know after 21 years, my population is going to be 7,000. And that's going to end up being, because t equals 0 represented 2,000, that's going to be in the year 2021. Now let's take a look at an exponential decay, and we'll use the idea of a half-life problem on this one. The half-life of radioactive iodine used to treat prostate cancer is 5 days. How long will it take the iodine to decay to 1.2% of the original amount? Okay, so what I know in this case, because I'm dealing with a percentage, I'm going to let my initial amount be 100%. So in this case, I'm using the exponential model of a of t equals a for amount, the initial amount e to the RT. It's very similar to what we just had. And so I'm going to let my initial amount be 100. So I have a of t equals 100 e to the RT. Now this is where the half-life comes into play. I know after 5 days I will have half of what I started out with. So since I'm starting out with 100, I know when t is 5, a of t is going to be 50. So I can say 50 equals 100 e to the 5r power. Solving for the exponential, I divide by 100, and I get e to the 5r is equal to 1/2. Taking the natural log of both sides, I get 5r equals the natural log of 1/2. So r is equal to the natural log of 1/2 divided by 5, which is about equal to negative 0.1386293, or approximately, I'm going to use negative 0.1386. So I now have a model for this situation. I have that my model A of t is equal to 100 times e raised to the negative 0.1386 t power. So in this case, what I want to do is I want to know how long it's going to take to go and decay to 1.2%. So again, in this case, I'm going to let A of t be 1.2, and I need to solve for t. So when I do that, the first thing I'm going to do is solve for the exponential like I've been doing. I divide by 100. So e to the negative 0.1386 t is equal to 0.012. Taking the natural log of both sides, I get negative 0.1386 t equals the natural log of 0.02. Solving for t by dividing by negative 0.1386 putting it in the calculator, I get that's about 31.911. So I know that it's going to take about 32 days for the iodine to decay to 1.2% of its original amount. The next one we're going to look at is a Gaussian model. Okay, and now in this case, some of the ones that we have, it's going to be more along the lines of plugging things in to this one, and that's really what's happening on this one here. You're plugging something in for x and finding out what n is. We're going to suppose an exam has a normal or bell-shaped grade distribution with an average score of 80. An approximate function for that models the class grade distribution is n of x equals 10e to the negative x minus 80 squared over 16 squared. Now, n is the number of students who received a score of x. So what we want to do is we want to approximately find out how many students scored 70. So what I'm going to do is I'm going to put 70. Remember, the score is x. So I'm going to put 70 in for x. So n of 70 is going to be 10 times e to the negative quantity, 70 minus 80, that quantity squared, divided by 16 squared. So when I put that exponent into the calculator, I get that this is equal to 10e to the negative 0.390625. And plugging that then into the calculator, when I finish up that calculation, I get that that's about equal to 6.7663. So I know that there's going to be about 7 students that scored a 70. Now I rounded that off using standard rounding. I rounded it up to 7. Sometimes some of you might not necessarily look at that way, and you would just truncate it. You drop off the decimal point and say 6. I would accept either answer on this one, however you want to look at it. Either 7 or 6 would be correct in this case. Our next model is the logistic growth model. Now, again, this one right here really looks at population growth over an extended period of time because all populations cannot grow completely exponentially all the time. Eventually, there are going to be issues that come into play, space and food being some of the bigger ones. So the logistic growth model really looks at that long-term growth, but it also can be used to model things like spread of a flu virus, like this example here, but we can also look at when we look at a carrying capacity of a habitat, how many deer can a habitat support? How many fish can a pond support? Those would all be logistic growth models because we would look at an upper. You'll find if you graph these out, you'll see that there are 2 asymptotes associated with it. We'll talk a little bit about those in class on Monday or Tuesday. Well, in this case, what we're looking at, we're going to look at a spread of a flu virus, and it's going to be modeled by the equation y is 1,000 over 1 plus 990 e to the negative 0.7 t power. Now, y is the total number of people infected after t days. So I want to know is how long is it going to take for 530 people to be infected. So what I do is I put 530 equals 1,000 over 1 plus 990 e to the negative 0.7 t. And what I have to do on this one, I need to go through and multiply through by the denominator. So I have 530 times the quantity of 1 plus 990 e to the negative 0.7 t power equals 1,000. I then divide by 530 and then subtract 1. and I'll get 990 e to the negative 0.7 t equals 1,000 over 530 minus 1. I divide by 990, and when I put all of this into the calculator, I now get that e to the negative 0.7 t equals 8.957 times 10 to the negative 4. Taking the natural log of both sides, I get negative 0.7 t equals negative 7.0178. Dividing by negative 0.7, I find that it's going to take, that t comes out to be about 10. So I know after 10 days, it's going to take 10 days, and after that 10 days, 530 people are going to be infected with this particular flu virus. Now let's take a look at the logarithmic model. Now in this particular logarithmic model, it's going to look very kind of different from what I mentioned, I showed in the beginning. But the book goes through the development of this formula, and it's really it's a formula to determine the amount of time it's going to take to pay off a loan. And so this formula gets used on a few problems in the book, so I want to spend some time going through the calculations necessary to do that. Well, what we have here to start out with is that we have to recognize P is going to be the principal. R, capital R, is your payment. How much what is that monthly payment that you're making? Little r is the annual interest rate. N is your payment periods. I is basically the interest that's going to accumulate, the interest rate over those payment periods. So it's going to be R divided by N. And T is time in years. And so what I know is that my payment is equal to the principal times I over 1 minus the quantity of 1 plus I to the negative nt power. And so what we're going to do on this one is we're going to end up taking this and solving it for t. So this one right here looks a lot like the logistic growth model we just talked about. And so you'll see the process I'm using to go and simplify this is actually very similar to what that was. I'm going to multiply through by the denominator, and I get r times the quantity of 1 minus the quantity 1 plus I to the negative nt power, and that's going to equal p times I. Distributing the r, I get r minus r times the quantity of 1 plus I to the negative nt power equals pi. And what I'm going to do now is I'm going to go and subtract that r from both sides. And so when I do that, I have negative r times the quantity of 1 plus I to the negative nt power equals pi minus r. And now I divide by that negative r. And when I simplify that, I get 1 plus I to the negative nt power equals 1 minus pi over r. Taking the natural log, because remember, I want to solve for t. Right now, t is in the exponent. I've got the exponential I've solved for that exponential. I now take the natural log of both sides. So when I take the natural log, I get that, and I can now bring that negative nt out in front. So I have negative nt times the natural log of 1 plus r equals the natural log of 1 minus pi over r. And then so solving it for t, I'm going to divide both sides by a negative n times the natural log of 1 plus I. So I get t equals negative natural log of 1 minus pi over r over n times the natural log of 1 plus I. Now please recognize here that I am not asking you to go and redo this. I'm just showing you in this particular point, and it is also going through and explained in the book. On page 401 shows you how they went from this formula here to the formula that you're going to be using to go and calculate the loan payoff information. So right now, this is where I'm at. Now keep in mind, I is r over n. And so when we go to the next side, so I know if t represents the amount of time needed to pay off a loan, then t is negative ln of 1 minus pi over r, capital R, all over n times the natural log of 1 plus I. But now replacing I with r over n, I get this formula right here, that t is equal to negative natural log of 1 minus p times little r over n times capital R, all over n times the natural log of 1 plus little r over n. That is our formula that we're going to be using to determine how much time it's going to take to pay off a particular loan. Let's take a look at an example here. We have Will owes $6,500 on his credit card, and the annual interest rate on that is 21%. What we want to know is how long will it take him to pay off the credit card balance if he pays $200 per month. Notice on here we're talking that he's just paying off on the balance. He is not making any additional purchases. So it's literally like he's got this thing gone up. It's sitting at $6,500 and he decides, okay, I'm not going to use it anymore. And I'm just going to go and pay $200 per month until this thing is paid off and it's down to zero. And I want to know how long is it going to take to do this. So we know we're using this formula that we just derived, that t is equal to the negative natural log of 1 minus p little r over n times capital R over n times the natural log of 1 plus little r over n. Well, in this case, capital P is what we start out with. That's $6,500. Capital R is our payment. That is $200 per month. Because we're paying per month, little n comes out to be 12, and R is 21%, but because we need to write that as a decimal, it's going to be 0.21. So, in this case, I know T is negative natural log times the quantity of 1 minus 6,500 times 0.21 over 12 times 200 all over 12 times the natural log of 1 plus 0.21 over 12. Putting the two things that are inside the natural log into the calculator and getting a decimal for each one, I get t is equal to negative natural log of 0.43125 over 12 times the natural log of 1.0175. Going through, putting that all into the calculator is going to give me something that's just slightly over 4. So I'm going to say it's going to take him 4 years to pay off this credit card. He has $6,500. He's paying $200 per month. So it's going to take him 4 years to pay this thing off. Now that may not sound so bad, but keep in mind that at $200 per month, he's going to pay for 4 years, that's 48 months, he's going to pay $9,600 on this. And since he owed $6,500, in 4 years he's going to pay $3,100 in interest. So that's quite a bit of money there, and that's part of the reason that you have to be careful with credit cards. The 21% interest is not something that is way out of line. A lot of people, especially young people, when they start out when they get their first credit card, that credit card is going to be sitting right around 21%. So please keep that in mind as you get older and start using credit cards. So that's my little speech in terms of financial aspect. So keep that in mind. But in class next time, we'll take a look at a couple more examples of some of these models, but most of the time is going to be spent with you going through using the models to go and answer questions. Also, please understand that a lot of times the base form of the model is going to be given to you. So it's not necessary that you're going to have to go through and say which one is a Gaussian, which one is that. They will actually kind of tell you which one you're working with, and you're going to try to fill in the constants and fill in the values, the missing values in there. So with that, I hope you've enjoyed your Thanksgiving, and we will pick this up on the Monday after Thanksgiving or for B days, or the Tuesday after Thanksgiving for A days. So again, hope you enjoy yourself, and we'll see you in class.